The universe once felt predictable, like a giant clock wound by a divine hand. Isaac Newton in the 17th century gave us the laws of motion, the rules of gravity. These laws painted a picture of a deterministic universe. With Newton's equations, we could predict the motion of planets. We understood the dance of celestial objects. The universe was a machine, and we were starting to learn its gears. This Newtonian view dominated science for centuries. It was a comfortable truth, a universe governed by elegant laws. But the universe, as we would soon discover, had other plans. As scientists delved deeper into the microcosm, they stumbled upon mysteries. The behavior of light and atoms did not obey Newton's laws. The clockwork universe, it seemed, had a few loose screws. Classical physics, the physics of Newton, could not explain these anomalies. A new theory was needed, a theory that could delve into the heart of matter and energy. The stage was set for a revolution, a quantum revolution. The 20th century ushered in an era of scientific upheaval. Brilliant minds like Planck, Einstein, Bohr, Schrödinger and Heisenberg emerged. They would forever change our understanding of the universe. Max Planck, a German physicist, was studying the energy emitted by heated objects. He found something unexpected. Energy wasn't continuous, flowing like water from a tap. Instead, it came in tiny packets, like grains of sand. Planck called these packets quanta. This was a radical idea. Energy was quantized, meaning it could only exist in discrete amounts. This discovery in 1900 shook the foundations of physics. Planck's quantum theory was met with skepticism. It was a bizarre concept, a departure from everything known about energy. Little did anyone know this was just the tip of the iceberg. Albert Einstein, a young patent clerk at the time, took Planck's quantum theory and ran with it. He used it to explain another puzzling phenomenon, the photoelectric effect. The photoelectric effect is the emission of electrons from a metal when light shines on it. But not just any light. Only light above a certain frequency could knock out electrons. This made no sense in classical physics. Einstein, in 1905, proposed a revolutionary idea. Light itself was quantized. Light wasn't just a wave, it was also a particle. These particles, called photons, carried energy in discrete packets, just like Planck's quanta. Section 5. Bohr's atomic model, a quantum leap forward. Niels Bohr, a Danish physicist, tackled the atom's structure. He used quantum theory to explain why atoms emit light at specific frequencies, creating unique spectral lines. Bohr proposed that electrons in an atom could only occupy specific energy levels, or orbits. These orbits were quantized, meaning electrons could only exist at certain distances from the nucleus. When an electron jumped from a higher energy level to a lower one, it emitted a photon of light. The energy of this photon corresponded to the difference in energy between the two levels. This explained the spectral lines. Section 6. Schrödinger's wave equation, embracing uncertainty. Erwin Schrödinger, an Austrian physicist, entered the scene. He developed a mathematical equation that described the behavior of quantum particles like electrons. It was called the wave equation. Schrödinger's equation treated particles as waves, not like tiny billiard balls. These waves, however, were not physical waves, but waves of probability. They described the likelihood of finding a particle at a particular place and time. This wave-particle duality was revolutionary. It meant that the position and momentum of a particle could not be known with absolute certainty. The universe, at its fundamental level, was inherently uncertain. Section 7. Heisenberg's uncertainty principle, the limits of knowledge. Werner Heisenberg, a German physicist, formalized this uncertainty. He proposed the uncertainty principle. This principle stated that the more precisely we know a particle's position, the less precisely we can know its momentum and vice versa. This wasn't a limitation of our measuring instruments. It was a fundamental property of the universe. The act of observation itself influenced the behavior of quantum systems. The uncertainty principle shattered the deterministic view of the universe. It meant that the future was not preordained. There was an inherent randomness, a fuzziness at the heart of reality. Section 8. Quantum mechanics reshaping our reality. Quantum mechanics, born from these groundbreaking discoveries, painted a bizarre and counterintuitive picture of the universe. It was a universe where particles could be in multiple states at once, where they could tunnel through barriers and where entanglement linked their fates across vast distances. This new physics challenged our classical intuitions. It forced us to rethink our understanding of reality itself. The universe was stranger, more wonderful than we could have ever imagined. Quantum mechanics was more than just a theory. It was a powerful tool that would pave the way for groundbreaking technologies, transforming our world in ways we are only beginning to understand. Section 9. The Quantum Future, Technology and Beyond. The impact of quantum mechanics on technology is undeniable. From lasers and transistors to medical imaging and quantum computers, our modern world is built on the principles of this strange and beautiful theory. Quantum computers, still in their infancy, promise to revolutionize fields like medicine, materials science, and artificial intelligence. They harness the power of superposition and entanglement to perform calculations that are impossible for classical computers. As we delve deeper into the quantum realm, we unlock new possibilities. We are on the cusp of a new technological era, an era fueled by our understanding of the universe's most fundamental secrets. But the journey doesn't end there. It's a journey of endless exploration and wonder. The universe, through the lens of quantum mechanics, continues to surprise us, to challenge us, to remind us that the greatest discoveries are often the ones that question everything we thought we knew.